This video lecture continues the previous one about complex numbers with some more details about operations with complex numbers. Let us suppose we have two complex numbers, z1 and z2, with z1 equal to a plus jb and z2 equal to c plus jd. Then the sum of the two numbers, z3 equal to z1 plus z2, is given by a plus jb plus c plus jd, which is equal to a plus c plus j b plus d. So the sum of the two complex numbers is a complex number with real part a plus c, which is the sum of the real parts of z1 and z2, and imaginary part b plus d, which are the imaginary parts of z1 and z2. So real part of z3 is equal to a plus c, which is real part of z1 plus real part of z2, and the imaginary part of z3 is equal to b plus d, which is the imaginary part of z1 plus the imaginary part of z2. The sum of two complex numbers can also be performed graphically by representing the two complex numbers through a Cartesian representation. So for instance, z1 is a point in the complex plane with coordinates a, the real part, and b, the imaginary part. z2 is a point in the complex plane with coordinates c, the real part of z2, and d, the imaginary part of z2. The complex number sum of z1 and z2, we have coordinates a plus c on the real axis and b plus d on the imaginary axis, which will identify the point z3. In a fully equivalent way, the sum of the two numbers can be regarded as the addition of two vectors, one identified by the point z1, the other one identified by the point z2, leading to a vector identified by z3. Given two complex numbers z1 and z2 with Z1 equal to A plus JB and Z2 equal to C plus JD. The difference between the two numbers is a complex number given by A plus JB minus C minus JD, which is equal to A minus C plus J B minus D, where A minus C is the real part of the difference between the two numbers and B minus D is the imaginary part of the difference. We can, of course, write in an equivalent way that the real part of Z3 is equal to the real part of Z1 minus the real part of Z2, and that the imaginary part of Z3 is equal to the imaginary part of Z1 minus the imaginary part of Z2. As we did in the case of the sum of two complex numbers, also here we can implement the difference between Z1 and Z2 graphically by means of their Cartesian representation in the complex plane. So as before, Z1 we have coordinates A, the real part, and B, the imaginary part, and Z2 will have coordinates C, its real part, and D, its imaginary part. The point resulting from the difference between Z1 and Z2 will have coordinates A minus C and B minus D. The point Z3 can also be seen as resulting from the difference between two vectors, one identified by the point Z1 and the other identified by the point Z2. The difference between Z1 and Z2 corresponds to the sum of Z1 and minus Z2. Minus Z2 is identified by the pair of coordinates minus C minus D. The sum of Z1 and minus Z2 will lead to Z3. Given two complex numbers, Z1 and Z2, with Z1 equal to A plus JB and Z2 equal to C plus JD, the product of Z1 times Z2 is again a complex number, Z3, given by A plus JB times C plus JD, which gives AC plus JBC plus JAD plus J square BD, which is equal to AC minus BD. Recall that the square of the imaginary unit is -1, plus JBC plus AD. So the product of the two complex numbers has a real part given by AC minus BD and an imaginary part given by BC plus AD. The product of two complex numbers is more easily performed if the two numbers are provided with a polar representation. So let's assume Z1 and Z2 are two complex numbers with Z1 given by the modulus rho 1 times the exponential of j the phase phi 1, and Z2 is equal to rho 2 times the exponential of j phi 2. The product of the two numbers will be a complex number Z3 given by rho 1 times e to the j phi 1 times rho 2 times the exponential of j the phase phi 2. This is equal to rho 1 times rho 2 times the exponential of j phi 1 plus phi 2. This corresponds to a complex number with a modulus rho 3 and a phase phi 3, where the modulus rho 3 is the product of rho 1 and rho 2, and the phase phi 3 is the sum of the phases of the complex numbers Z1 and Z2. The result on the phase has been obtained by simply applying the product property for exponents. Let's assume now that rho 1 is equal to 1 and also rho 2 is equal to 1. Then Z1 is simply equal to e to the j phi 1 and Z2 is equal to e to the j phi 2. Z1 is a point in the complex plane on the unit circle at an angle phi 1 with respect to the real axis. Z2 also is a point on the unit circle forming an angle phi 2 with the real axis. By multiplying Z1 by Z2, we simply move Z1 counterclockwise along the unit circumference by an angle phi 2. given two complex numbers, z1 and z2, with z1 equal to a plus jb and z2 equal to c plus jd, the ratio between the two numbers, z3, is also a complex number, which can be calculated as a plus jb divided by c plus jd. We then rationalize the denominator, which means that we multiply both the denominator and the numerator by c minus jd. So the numerator will be a plus jb times c minus jd. By performing the multiplication at the numerator and at the denominator, we get AC plus JBC minus JAD minus J square BD divided by C square plus JCD minus JCD minus J square D square. Plus JCD and minus JCD at the denominator simplify, and then recalling that the square of j is minus 1, we get AC plus BD plus J BC minus AD at the numerator and C square plus D square at the denominator. And eventually we get AC plus BD over C square plus D square as the real part of the ratio plus J BC minus AD divided by C square plus D square, where BC minus AD divided by C square plus D square is the imaginary part of the ratio. As I already mentioned, the ratio between two complex numbers is more easily calculated if the two numbers are provided with a polar representation. So let's assume we have two complex numbers, again z1 and z2, with z1 equal to the modulus rho 1 times the exponential of j the phase phi 1, and z2 is equal to rho 2 the exponential of j phi 2. Then the ratio between the two numbers is again a complex number given by rho 1 times the exponential of j phi 1 divided by rho 2 the exponential of j phi 2. This is equal to rho 1 over rho 2 times the exponential of j phi1 minus phi2. So eventually, Z3 is a complex number rho 3 e to the j phi 3, where the modulus rho 3 is equal to the ratio between the moduli of the two complex numbers z1 and z2, and the phase phi 3 is the difference between the phases phi 1 and phi 2. The result for the phases were obtained by applying the quotient rule for exponents. Let us assume now that the moduli of the two complex numbers are both equal to 1, as we did in the case of the product of complex numbers. So let's assume that rho 1 is equal to rho 2 is equal to 1, in which case z1 is equal to e to the j phi 1 and z2 is equal to e to the j phi 2. Both z1 and z2 are represented in the complex plane by points on the unit circle. The ratio between z1 and z2 gives again a point on the unit circle as the modulus of the ratio, rho 3, which is rho 1 over rho 2, is equal to 1. The phase will be phi 1 minus phi 2. So, the effect of dividing z1 by z2 is that of moving the point z1 clockwise along the unit circle by an angle phi 2. We have already defined the modulus of complex numbers when discussing their possible geometrical representation in the complex plane. Here, we will define the modulus as a function of a complex number. Given a complex number z1 with z1 equal to a plus jb, then the modulus of z1, which is indicated with this symbol, is equal to the square root of the square of the real part plus the square of the imaginary part. This definition is of course compliant with the geometrical definition we gave for the modulus of a complex number as the distance from the origin of the point representing the number itself in the complex plane. Note that if z2 is also a complex number, then the modulus of z1 times z2 is equal to the modulus of z1 times the modulus of z2, and the modulus of z1 divided by z2 is equal to the modulus of z1 divided by the modulus of z2. Let's assume z1 is a complex number with z1 equal to a real part a plus j and imaginary part b. Then the conjugate or the complex conjugate of z1, indicated by z1 with a bar over it or by z1 with an asterisk, is given by a complex number with the same real part and an imaginary part of equal magnitude as z1 but opposite in sign. Let us compute z1 times its complex conjugate. So z1 times the conjugate of z1 is given by a plus jb times a minus jb. which is equal to a squared plus jab minus jab minus j squared b squared, which eventually gives a squared plus b squared. If we now recall the definition of the modulus of Z1, we see that Z1 times its conjugate is equal to the modulus of Z1 squared. So another possible definition of the modulus for a complex number is given by the square root of the complex number times its complex conjugate. We already know the phase of a complex number as a geometrical feature of the complex number itself in a complex plane. The phase, also called the argument of a complex number, can also be seen as a function of a complex number, producing as a result the angle or phase of the number itself. So if Z1 is a complex number with Z1 equal to rho 1 e to the j phi 1, then the argument of this complex number, indicated with the symbol phase of Z1, or alternatively by the symbol argument of Z1, is equal to phi 1. If Z2 is also a complex number with Z2 equal to rho 2 e to the j phi 2, then the argument of Z1 times Z2 is equal to the argument of rho 1 rho 2 e to the j phi 1 plus phi 2, which is equal to phi 1 plus phi 2. So the argument of the product Z1 times Z2 is equal to the argument of Z1 plus the argument of Z2. On the other hand, the argument of the ratio between Z1 and Z2 is equal to the argument of rho 1 divided by rho 2 e to the j phi 1 minus phi 2, which is equal to phi 1 minus phi 2. So the argument of the ratio between Z1 and Z2 is equal to the argument of Z1 minus the argument of Z2. Suppose now that the complex number Z1 is provided in a Cartesian form. So Z1 is equal to A plus JB. Note that for positive values of the real part, the phase phi 1 can go from minus pi divided by 2 to pi divided by 2. Instead, for negative values of the real part, the phase can range from pi divided by 2 to 3/2 pi. Finally, note that if A is equal to 0, then the phase phi 1 is equal to pi divided by 2 if B is positive, while it's equal to minus pi divided by 2 if the imaginary part is negative. This latter case we have considered is the case of purely imaginary numbers, which is complex numbers with real part equal to 0. We have already used the inverse tangent function to calculate the phase of a complex number. In particular, we said that if z1 is a complex number with Cartesian representation a plus jb, then the phase phi 1 of the complex number is given by the inverse tangent of the imaginary part divided by the real part. This result, as I already mentioned, is actually true only if A is positive. The reason for this limitation is that the inverse tangent function can only take values between minus pi divided by 2 and pi divided by 2, which is the interval of values that the phase can assume for positive real part only. Actually, the inverse tangent function asymptotically approaches pi divided by 2 for x going to infinity and minus pi divided by 2 for x going to minus infinity. So let us consider now a complex number z1 with z1 equal to a plus jb and a negative. Note that if a is negative, then we can write that a is equal to minus the absolute value of a. Of course, the phase of z1 is the angle phi 1, which is for sure larger than pi divided by 2. Let us compute now the inverse tangent of b over a. So the inverse tangent of b over a is equal to the inverse tangent of b over minus the absolute value of a, or the inverse tangent of minus b over the absolute value of a. This, of course, is different from phi 1, but is equal to the phase of a complex number with real part the absolute value of a, which is equal to minus a, and imaginary part minus b. This phase is phi 1 prime. Note that the phase phi 1 of the complex number z1 is equal to pi plus the inverse tangent of the imaginary part b divided by the real part a. Given the fact that the exponential function e to the j phi is a periodic function with period 2 pi, this is also equal to pi plus the inverse tangent of b divided by a minus 2 pi, which is equal to the inverse tangent of b divided by a minus pi. It is worth emphasizing again that This result is valid when the real part of the complex number A is negative. So to summarize, given a complex number Z1 with Z1 equal to A plus JB, the phase of Z1 is equal to the inverse tangent of the imaginary part divided by the real part of the complex number for any real B and for A larger than 0 is equal to pi divided by 2 for positive imaginary part and real part equal to 0 is equal to minus pi divided by 2 for negative imaginary part and again real part equal to 0, and finally is equal to the inverse tangent of b over a plus pi for any real value of the imaginary part and for negative values of the real part. The phase of the complex number 0 or 0 plus j times 0 is not defined. Suppose Z1 and Z2 are two complex numbers. Remember that a complex number can be written in a rectangular form or in a polar form. So Z1 can either be written as A1 plus J B1 or as rho 1 e to the j phi 1, while Z2 can either be written as A2 plus j B2 or as rho 2 the modulus times e to j phi 2 the phase. So when we write an equation like Z1 equal to Z2, what we actually mean is that the real part of Z1, which is A1, must be equal to the real part of Z2, which is equal to A2, and that the imaginary part of Z1, which is B1, must be equal to the imaginary part of Z2, which is equal to B2. Or equivalently, we may mean that the modulus of Z1, which is equal to rho 1, is equal to the modulus of Z2, which is equal to rho 2, and that the phase of Z1, which is equal to phi 1, is equal to the phase of Z2, which is equal to phi 2. So an equation in the complex field always translates into a pair of equations in the real field.
For these complex numbers, find the position in the complex plane and compute the modulus and the phase.